Yep, we got it. Gotcha.
Okay, what we came from, let's do it this way. If you go to the website and then you come down here to where it says Edway, and you click on Edway, this is the screen that we're on right now. Okay. And in this particular case, as today's date, review of series and parallel circuits. This is where we're going. Now, I might remind everyone that, first of all, we used to have an expression because when we were teaching a lot of this, we'd say, okay, anything that's an illity or an ivity is a property. And you say, where are you going with this? Well, like conductivity versus conductance. Conductivity is a property. Conductance is a measurable value. Well, then resistivity is a property and resistance is the value. And you also have some other things. There's a lot more than just this. These are just samples. Reluctivity versus reluctance. You've got permeability versus permeance. Okay, these are all properties, and we need to remind ourselves of some of this because there are areas of conductance when you get into tubes and FETs. If we ever do that, for instance, there's an area called transconductance. And the transconductance is actually two words. It's transform conductance is really what it comes into. Well, we can save that for later, but let's do this. Illustration number 1. Here we go. By the way, these are all legitimate test questions. So if you're helping someone, you can download these. Feel free to do so. Download these and they can fill in values. This requires the calculator. However, remember, you're teaching people. And this is the area I talked about before when I said, those of us that are from a technical background, we'll look at this and we say, okay, this is really, really simple. Wait a minute, understand that there are some people, this is totally new and it's a brick wall. I'll give you an example. In the Federal Way area, there was a fellow who is now an acquaintance of mine, but I didn't know him at the time. He decided to get into ham radio, so he studied and took his technician test and passed it, no problem. Then they said, well, would you like to try the test for general? And he says, sure. So he took the test for general. He thought he was doing okay until he got to the electrical part. He says, then it was like a brick wall. So somebody said, well, why don't you get a hold of Dave? So they pointed at me and I spent some time with him. And then sometime later, after going a few of these things here, he passed his general and he's really happy. But he said at the time when I was helping with this is so strange to him, he had a hard time getting his hand or his head around it. Okay. All right. Now let's get into something here. First of all, if you are helping somebody, you're not just teaching how resistors and series add, but what you're also doing is you're saying, look, as current flows, it can go left to right, right to left, but also because the current is common between these two elements, it is going to then cause an IR drop, which is the key word for saying voltage drop. This 2K resistor and this almost 4K, that means that the voltage drop across this R2 is going to be proportional to this one here. In fact, is mathematically, it's direct proportional. The voltage drop across R2 is going to be nearly twice as much as the voltage drop across R1, whatever it happens to be. Well, then if we look down here, we can actually say, all right, if the current is 10 milliamps or 18 milliamps in this case, 18 milliamps will be a multiplier for each of these resistances to cause a certain amount of voltage across each one. So the voltage here across R2 is going to be twice as much across R1. All right. Now, you'll notice that A and B are not connected to anything except B is connected to ground. Then where does this come from? Well, it was suggested to me by my good friend Walt that I should show that this circuit really comes out of another circuit. So what I did is I say, okay, here's a box which represents a whole lot of complex circuits. And this guy here, these 3 resistors are inside that box. And that's where it comes up here. So why is this important? Well, because I'm trying to point out to them that this could be a negative voltage and this could be a positive voltage. Now we're talking potentials. We're not just talking about IR drops, we're talking about potentials. Now, usually when we start teaching someone about Ohm's law, we start off and just show them how simple it is to just add the resistances. Fine, okay, add the resistances. Then you can also say, if you knew what the voltage was between A and C, then you could figure out how much voltage there is altogether. Well, how do you know that? Well, because this current is what goes through both resistors. By the way, as current is flowing this direction, that means that C is going to be more negative with respect to ground, whereas point A, I turned off my radio here, hold on. Point A is going to be positive with respect to ground. So potentials are with respect to ground. You come up here to this one, where's ground? I've actually had people get mad at me because they said, where's ground? And I said, it's somewhere else. And I said, well, it's unsolvable then. No, I beg your pardon. This potential is stated with respect to ground somewhere else. Well, guess where ground is? It's in this circuit somewhere. Now, if you'll notice at this, also there's something else. Somewhere between this -3 volts and this positive 9 volts almost is a ground potential. And somebody says, oh, you mean ground is there? No, no ground, but ground potential. That's going to be a 0 volt somewhere in that resistor. All right, but if you have this voltage which is below ground and this voltage here which is above ground, that says there's about a 12 volt difference between those two. And that's the voltage across this resistor, which allows you therefore to compute the amount of current. But because this is negative, this is positive, that means current is flowing left to right in this drawing. So anyhow, you can figure this out and you can say, okay, now this 9K here is like almost 5 times the current, the voltage over the resistance over here, which means then there is a direct proportion. You see where I'm going with this. 12K, it's what, 3 times as much? So therefore the voltage IR drop, the voltage drop across this resistor is going to be about what, 6 times this voltage drop or IR drop here. Now, I don't know if you caught this, but I keep saying IR drop because a lot of times when you're helping somebody to learn, you have a tendency to only talk about a voltage drop. But by using the term IR drop interchangeably, bounce back and forth, what you're doing is you're reminding this new person that we're trying to learn all this, that IR is current times resistance, and that formulates the formula for, guess what? IR drop is the voltage drop. So what I found is that when I'm helping someone, I tend to blend terms in to get them to where they hear the term so it doesn't catch them by surprise sometime later. So I'm using IR and voltage drop at the same time. There's also something else that I have done for years. You'll notice that these resistors are not nice even values. They are deliberately picked as common values. Now I do this on purpose. The reason why I do is because in the classroom I found that when I do this, day after day, people get used to seeing these and they recognize these numbers. They've seen them before. So I stay away from what a lot of textbooks do, and I don't like it. They use nice even numbers. Well, I beg your pardon, but that's not what we find in the real world. There's more of these kind of numbers than what there is nice even numbers. Does everyone see where I'm coming from on this? Okay. So what I'm really doing is I'm mixing some of my terminology early in the game so that it's not a major surprise when I spring it on them later. So I mix it in there to begin with. Now here again, this is a simple circuit, but for a beginner, you'd be surprised at what kind of a block this is for their thinking. So you have to take your time and make sure that they understand some of these what we think is very basic principles. But remember now, all of this is not just simply DC review, but I put things together so that you can use it as a teaching material. Because sooner or later, hopefully, you'll run across somebody that says, hey, I want to get a ham license, but I don't know anything about Ohm's law. Can you help me? So here you go. This is resource material that you can feel free to download and use accordingly. All right. Everything is prepared that way. By the way, again, this is a legitimate test. That is a quiz or a test, and you can use it as such as a worksheet to teach with. Here we go, next diagram. Illustration number 2. Here we go. Now we have a parallel circuit. Now, in this parallel circuit, we have a problem. people look at this formula down here and they say, that's kind of complicated. What are we doing? All right, now back in the slide rule days before calculators, we did the product over sum. This circuit right here, that is this formula here, does not work well with the calculator. You can do it, but with calculator, I'm sorry, with the slide rule, it was a pain. But the thing is with the calculator, it's just a piece of cake. However, just punching buttons doesn't help you understand it. Now, this is a good time for me to bring up something else. When you see a resistor, you say, well, that's resistance. But now also, this is a good time to remind, well, yourself as well, this is also a conductor. You say it's a resistor. It also is a conductor. And by the way, when you see a wire, oh, that's obviously a conductor. But bear in mind that as a conductor, it also has resistance. And now is the time to point out that the difference between a conductor and a resistor is a reciprocal relationship. By the way, anybody know what conductance is measured in? Mhos. Mhos, which is ohms spelled backwards. Mhos. So what we've got here, see this reciprocal value? This is camouflage for conductance. What you really got here, you say, I got two resistors in parallel. But wait a minute, look at it from this way. You have two conductors in parallel. And the total conductance is simply going to be the summation of the conductive values. You say, well, I thought we were doing parallel resistors. Yeah, but they're also parallel conductors. So down here, this formula in reality is conductance of the first resistor adds to the conductance of the second resistor, and you have the total conductance. However, to get it to resistance, you have to do the reciprocal. That's why this 1 is over the whole thing. That's exactly where this formula comes from. Now, I have to be honest and say that in my early years of teaching, I don't think I pointed this out. It wasn't that I didn't know it, I just didn't see the value in it. So here, I'm making a big point of the fact that this formula is based on conductance, which is what this is. You say, well, it's 1 over R. Yeah, that's G for conductance, and that is the correct term. G1 plus G2 reciprocal is RT. Coming over here, this is why it works over here. You're actually adding conductances. So you got the conductance of this one, plus the conductance of this one, plus the conductance of this one, add it all up together and do a reciprocal. And you know what? That's where this formula comes from, and you have RT. For instance, the conductance of R1 is 500 micromhos. There's your mhos. The conductance of R2, since it's more resistance, is less conductance. And here it is. Oh, there it is, 256.4 micromhos. Do you see where we're going on this? So what I'm really doing is I'm explaining this formula, which really messes people up when they first run into it. And over here on this one, it's just, well, what have I got? 2.2K, and I don't have that calculated out, but you could do it with a calculator by putting in 2.2K and take the reciprocal. And that will give you the amount of micromhos. And then as you go to more resistance, it is less conductance, therefore less micromhos. And when you get up to 12K, it's a whole lot less conductance. But nonetheless, all three conductive values turn out to be G1 plus G2 plus G3, and the reciprocal is, guess what, RT. So that's where this formula comes from. Just kind of explaining then what a lot of people say, why do we use this formula here? Well, it's because what you're really doing is this is G1 in camouflage. This is G2 in camouflage. This is G3 in camouflage. When you add them, you have GT. Total conductance, but when you do the reciprocal, you've got, guess what, RT. You see that? Kind of a sneaky way of going about it, but you know what? I think if we point this out, we're actually helping someone to understand why this formula is this way. So it isn't just a matter of doing a whole bunch of math. It's how to figure things out. Now let's go back to something else. Here you have parallel resistors In the series resistors, current was common, but here it is parallel. That is, it is what? Voltage is common. They both have the same voltage. Now, 2K or 2.0K is more conductive than 3.9 by almost twice as much conductive. Therefore, it'll have twice as much current going through R1 as what goes through R2. So then you can figure this out based on that. And by the way, if you were to figure out with a common voltage, if you say, well, I don't even know what the common voltage is, you could just simply guess at one. Ignoring all of this, you could say, oh, let's put 10 volts across here. And with 10 volts, you know what this current is. With 10 volts, you know what this current is. Add the two currents. When you add the two currents, you know the voltage, you know the current. Hey, you can figure out the parallel resistance just based on what? Guess what? Ohm's law, without even figuring out their parallel values. So it's a good thing to spend time in this area, because as you spend time in this area, going through different avenues, people begin to get a grasp on what you're talking about. Going back to what I said earlier, you know, here, those of us that have come from a technical background, we look at this, we go, okay, piece of cake. No, it's not for somebody that's new at this. It really is something they can struggle with. So it is your job to simplify it as much as you can from many different angles as you can. Don't stick to just one angle, because if you do, you create a myopic situation. You don't want that. You want them to understand this overall. So hit it from 2 or 3 different angles. And when you do, you'll have somebody that begins to understand what's going on. Don't rush through this too fast, okay? Comments or questions, please? I know you're muted out, but feel free to jump in. So I don't know if you, go ahead and unmute. Go ahead.
Yeah, Dave, after doggone it, after all these years, where were you 40 years ago? Or whatever
Here,
it was. Oh my gosh.
So this, you can see the logic of where I'm going with this, right?
Yeah, amazing.
Well, another thing is this. Math is not my strong point. It's my weakest. And I've had to make do. I had a year, I had a student in Montana that said, where were you when I was in the 8th grade? And I said, well, probably teaching some of this stuff elsewhere.
Wow.
Anyhow, feel free to jump in, okay? Anytime. I really, to be honest with you, as many years as I have taught, I wanted my students in the classroom to jump in at any time. Question this, question that. Why do you do this? Why do you do that?
Sure.
Run over that again. I want them to do that. I'm comfortable with that. So like I said, jump in, okay? All right, now that we've done this, let's do something a little bit more interesting. This was illustration number 2. And here again, these are downloadable, printable, and they're available for helping other people. Here we go. That was illustration number 1 and 2, but let's go here to something else. Illustration number 1A. I'm going to show you something rather interesting. We know that in series, these resistors simply add up, so we have total resistance. What would happen if I told you, oh, by the way, forget that there are K ohms. Consider, if you will, that here are this 500 micromoles, that's this guy. Do they add? And the answer is no. Conductance does not add in series. Think about that. It does not add in series. How do you figure it then? Oh, come down here to this formula. The total conductance, does this familiar looking? Total conductance is if you take this 1 over G1 plus 1 over G2, that means reciprocal G1, reciprocal G2, add them together, do the reciprocal, you got GT. You say, whoa, wait a minute. Going to what you said a while ago, isn't this resistance in camouflage? See that? 1 over G1 is 2K. 1 over G2 is 3.9K. So what I'm trying to say is that this formula, awkward as it is, would be the proper way of figuring this circuit up here in conductance values. And you say, that's weird. Well, okay, I'm leading up to something. if we ever get around to discussing inductance and that is reactance for inductance, reactance for capacitance, you'll find that everything we learn about coils and inductors, then we turn around and we study capacitors, we'll find that capacitors are totally backwards or opposite from the coils. And guess what? Every combination, every circuit you learn where they have formulas, the formulas are all backwards. So what happens is when you put capacitors in series, this kind of a formula comes into play. However, you put capacitors in parallel with each other, well, then the capacitance adds. So up in here, put it this way, resistors in series makes more resistance, therefore isn't that less capacitance? I'm sorry, less conductance, slip of the tongue, sorry. Just something to kind of warp your mind a little bit, okay? When you have more resistors in series, that means you have less conductance. Now, in that same respect, if you're dealing with a true conductor, a length of wire, the longer the wire, it is what? More resistance and less conductance. Think of that. So that's why I keep bringing up conductance. A wire is a conductor. However, it also has resistance. So therefore, you have to be able to think both ways, all right? All right, let's go back to some other easier stuff, okay? Illustration number 3 is my favorite for years. Oh, I love this one. I have given this one to I don't know how many classes, and I'll tell you why. What I found is that just about the time that a newcomer thinks they got a handle on resistance and maybe even conductance, be it in series or in parallel, you really throw them in a loop when you start putting a circuit like this up here, because look at here, I have series, parallel, in series with this other series, which is parallel, and then in series over here. So guess what I'm doing right now with my poor students? I am flipping their mind back and forth between parallel one time, serial another time, back and forth, back and forth. Not only that, but somewhere in here, they have to worry about potentials and they have to worry about IR drops. Remember, an IR drop here is an IR drop of 9 volts. Why is it IR drop? I thought you said that was 9 volts. Yes, because this 9 volts is because of current times resistance, according to the formula, that pi symbol we give them, okay? So you say, oh, that means then if I know this is 9 volts and 7.5K, that means I got a little bit more than 1 milliamp flowing through that resistor. Aha, now you're catching on. So here we go. So here we know the resistance going, the current going through this resistor, because 9 volts and 7.5K, just a little over 1 mil, right? And then lo and behold, that current is the same over here through this resistor. So now we can get an IR drop here. And pretty soon then this collective IR drop and IR drop here is what is across this. So how much current is going to flow? Oh, well, to figure this out, you have to figure out these 2 resistors in series, put them in parallel with that, then in series with that to make a collective resistor. And when you have that one resistor, then you can figure out that the voltage between here and here is the same as between here and here. And now I can figure out how much current is flowing in that circuit. So you see, the whole thing is a deductive reasoning. This is a legitimate test. This whole thing right here, legitimate test. I've used this in the classroom for years. Notice I have the ground here. Since I have a ground here and current is flowing this way, then that means the point D over here is going to be positive with respect to ground, whereas as current is coming in this way, that means the point A is going to be negative with respect to ground. So now when they're all done, they'll have a potential at point A, point B, point C, and point D. Here again, that shows up over here as potentials. And by the way, if the student did not put a proper plus and minus sign on these potentials, I would mark it wrong. I don't give half points. I was known as a non-bending instructor. But you know what I found? I found if I was consistent in the classroom, then I found that the students would work harder, try to get it right. And they knew that I expected them to do it right all the time. And as a result, they put more effort into it. And you know what? They became better technicians. And as a result, I got good results with these problems, both this one. And if you'll notice here, I've moved the ground to a different point and I have the current going in another direction. Plus, I said, oh, by the way, you got 25 microamps flowing through that. Oh, 25 microamps. Wow, I'm not going to have very much voltage then across this 8.2K ohm resistor, am I? It's going to be in the order of millivolts. Okay, so here again, they had to properly identify everything in this circuit. This turned out to be a really good training exercise. And the students got to where they expected this kind of a challenge. And they did well. Comments or questions? In fact, you know what? I would encourage you guys just to download this guy here and figure it out. There's some deductive reasoning in here, and that's what it's intended for.
These are on the your website, Dave?
Yes. Yep.
Okay.
They're all coming off of this one page that's back here, this page here. They're all off of this page. Just come down here and click on them, and there it is. They're all downloadable, printable, and go from there. Now, at this time here, I want to point out something. Here again, I have intentionally forcing the individual to mentally adjust between going from serial to parallel to serial to parallel. To begin with, they have a difficult time doing that. And by the way, here again, I remind you, if you're helping somebody who is not in this area, this is all new to them, you'd be surprised how difficult this can be. They can spend all day trying to figure this out, and they need your help to go through it. So like I said, it's a legitimate problem, both of them. And it would be good to go through it just for, well, as the purpose of our presentation here, DC review. So it is a challenge. Don't be afraid to try it. And by the way, I think that these are worthwhile training vehicles, if you want to call them that. These are good training vehicles. They're intended that way. And these are from years of teaching. Questions? Yes, go ahead.
So in high school, they had all these formulas for resistance, and you try to remember them, you forget them. Is there a reference, not manual necessarily, but a place where you can find all these formulas so you don't have to not necessarily memorize them, just have quicker reference to them?
Well, actually, believe it or not, the only formula I used so far was the pi formula for E over IR,
okay,
the circle, and reciprocal for conductance. And that's it. That's all that we've gone through so far. There are other formulas later, but I introduce them easily one at a time, and I take time for everything to kind of soak in.
okay.
So that's actually the only two formulas here. And bear in mind, that's my weak area. So, yeah. All right. Well, let's go on to something a little bit more challenging, okay? Are you ready for this? Now that we've got this mastered, we'll move on to this, the infamous ladder circuit. That's this guy up here at the top. What I would do is I would draw this on the board. They don't see this down here, okay? They don't see this at all. They only see this diagram up here. And I say, okay, now look here, you got a whole bunch of series parallel stuff. And by the way, up here is a variable resistor that can go anywhere from 0, dead short, to infinity, which is an open circuit. And they say, oh, yeah, okay. But to make it easy for you right now, here's what we're going to do. I will assign a 3.9K right there. We'll use that. Said, now, all I just want to know the voltage drop across this resistor, the IR drop, if you please, and the amount of current going through it. And then what I do is I just stand back and watch and let it soak in. Guess what I'm looking for is their realization, say, there's a lot of calculations involved here. All I want is just this voltage. Oh, by the way, the amount of current going through, same thing. All right. And then after a while, they begin to think, what do we do to get that? And I said, well, actually, it's really simple. Let's take a look. Now I go ahead and run them through it. Now look, this resistor here is in series with this one and this one. That makes one resistor that sits out here. Oh, there it is right there. This is an equivalent resistance. Do you see that? Adding these three resistors together comes up to be 13.7K. That's a parallel with R5. But this is a conglomerate, if you want to call it that, of these three resistors. So guess what I've done? I've gone from a series circuit to now, a parallel circuit. Then when they put this in parallel, it comes out to be 4.5K, which is, guess what? In series with these two resistors. Which is 21.844K, which happens to be in parallel with this guy, which happens to be in series with these two guys, which comes out to be, lo and behold, well, a composite value across 18 volts. Do you see what I'm doing? In this left side over here, I'm saying series, parallel, series, parallel, series across this 18 volts. What have I done with my poor students? I have forced them to switch their mind back and forth between series and parallel. By the time we're through with this kind of a thing, they are very comfortable with it. But at first they might groan a bit. I've heard groans in the classroom. Now, you say, okay, so what are we after? Well, when I have a composite value here across 18 volts, I can tell you how much current's going to flow. Lo and behold, this composite value across here is, well, I'm going to have what? 439 microamps. Not a lot because of this 18 volts. But now you come up here and now you do something else. Look what we're doing here. Now we're going backwards. We're taking the current that we know, and we're saying that current is common in the circuit. Well, this is a parallel value. So that current is going to be right here dividing between these two. But guess what? There's a common voltage. So whatever this common voltage is the voltage you would use here in this circuit. So in other words, I have this parallel, but I have current division. And then I've got voltage across each resistor because that's the current through this equivalent, which is what these three are here. So then now that I know this current, I know the voltage across this resistor, which turns out to be this combination up here. Now that I know the voltage, I can apply the voltage here and the voltage here and get individual currents. So now I move my way up. And now that I know the current through this guy, that means that's the current through these three resistors right here. Hey, now that I know that current, I can say, aha, I know though, that's the current through this final resistor, 3.9K, and now I can compute the voltage across that resistor. Everybody with me? So what I've done on this circuit over here, I have forced the individual to go series, parallel, series, parallel, series, parallel, series. And then I go backwards. Now we're dealing with voltage division, current division, voltage division, current division, voltage division, current division, until you finally get up here and you know I have a series current and voltage across that guy. And now we finally know what it is. And you can then say, finally, after all these computations, I know the voltage the instructor wanted across that resistor. And just about the time there's this big sigh of relief, I said, didn't I tell you? I'm going to change that now. I'm going to change this from a 3.9 to, I don't know, maybe a 6.8K. And let that soak in. When I let that soak in, they say, wait a minute. You change that, you change everything. Yeah, only a little bit. See where we're heading on this? This is what they call the ladder circuit. Now, what's interesting here, wouldn't you like to know if there's a simpler way to do all this? There is. It is into an area by the technical name of a Thevenin's equivalent circuit or a Norton's equivalent circuit. Here's where we go. Here's what we start with. There is another process that we can do all of this and come up with something simpler. And then I'll explain why this is so important. By the way, this is commonly used in engineering circles for complex circuitry. Here's what you do. First of all, follow me with this if you will. I think you'll find this interesting. Pull off this resistor right here. If you pull off this resistor, that's an open circuit, and there's no current flowing through those two resistors. Would you agree with that? Therefore, if this is open, and you do all these kind of calculations like we did before, whatever the voltage is across R5 will be the same voltage out here as an open circuit, because there is no current flowing through 5.1K, no current flowing through 4.7K. As a result, the potential difference between these two is the same as across the 6.8K. So what happens is you go through this whole thing, but with this resistor pulled, all right? So here's what we're gonna do. We'll go down here to illustration number 5. Let's see, let me go to 6 instead, all right? Illustration 5A. I got an open circuit there, okay? What do? Well, to begin with, because these two resistors don't come into play, what you really have is this resistor in series with these two, which is parallel to this, which is series with this. So you work your way all the way down, and this time you come up with a similar current as to what we had before. What you're going to find is that what goes on out here at this point is only going to vary within certain points. Now here's where we're heading for all this. This circuit up in here is what we're heading for. See how we got 1 voltage, which is a whole lot different than this 18 volts? As it turns out, as you go through the circuit and figure it back up here, you'll find in this area here, the open circuit voltage. That's EOC. What it stands for is voltage of the open circuit variety. Okay, that's really what this is. 1.407 volts is the open circuit voltage. That's the voltage we use up here. So we now find that we can take this entire circuit and reduce it to this voltage. But see this resistor here? We still have to figure that out yet. I'll show you how that's done. If you were to put an ohm meter across these 2 points, you would destroy your ohm meter. But the way you do this, what you're really wanting to do is you're wanting to figure out what this circuit looks like with an ohm meter with the voltage pulled. So what you do is you pull the battery. And after you pull the battery, let's come down here to this guy. You pull the battery and replace it with its internal resistance. Now, even a battery has internal values, internal resistance. However, since this is a voltage source, which is known therefore as very low internal resistance, the resistance is so low compared with all these values, it's negligible. So therefore, we'll just put in here a short circuit to represent what is the internal resistance. Then we put our ohm meter across here. What would the ohm meter see? Well, actually, this time you work the problem backwards. See this? Come across here until finally you come up with this guy here in series with these 2 resistors that have no current flowing through them. And it turns out to be this value, 15.34K. And that is this guy right here. You now have a circuit which has the voltage we figured out as open circuit voltage and this resistance. And this resistance is the equivalent of this whole thing. If you were to take construct this on a breadboard and put an ohm meter across here, this is what you actually measure with an ohm meter. So what we've done, here's the point. We have taken this entire complex circuit with a tweakable, readjustable value, and we have reduced it to 2 parameters, a voltage and a resistance. As a result, you can now come out here and put anything you want out there. So let's see what that looks like. Let's go on down to illustration 5D. Whoops, that's not the one I want after all. We'll go back up to 5B. And notice what we've done. This is how we figured out the resistance. Let's go back to the right one, get my head on straight here. We come up to this guy here. Now, what's interesting is I can change this from a dead short to an open circuit. I can tell you what the values are going to be as a result. Put anything you want here. And now we've taken a complex circuit, this whole guy over here, and we have reduced it to very, very simple parameters. And we can project real quick exactly what to expect in terms of current and voltage. Okay. That's the way it works. This is called a Thevenin's equivalent circuit. Now, believe it or not, this technique is used in engineering practices for complex circuits to reduce them down to a simplistic representation. This circuit here represents this entire thing over here. It really does. It's going to seem like an impossible task, but no, it really does work. I was a little bit involved with something that was done at the Boeing Development Center. You fellows probably remember the Mobile Minuteman, don't you? That's where they're going to have the Minuteman missile on the train. Okay, it was my lab that McNamara came in. And from the technical side of technicians, I was the honcho for that. In fact, I'm the one that let McNamara in. We had a problem, a mysterious problem that showed up in all the control circuits. We had the launch command consoles in there. Everything was in there for firing a missile, right? The Minuteman missile off the train. There is one security box. We used to call it the tickle box. That's the one if the president punches in the codes to fire missiles, in retaliation or whatever, then the codes had to go into this one particular box, which had all kinds of security alarms on it. So if somehow signals were trying to come into the box that were not authorized, it would set off alarms like you wouldn't believe. We called it the tickle box. Well, what happened is we found an interesting situation, very frustrating. We found that some of the equipment was sending signals through the ground wires. And we had really good grounds on that setup. And these signals were going into the tickle box and setting off alarms. We spent a year, and I was just a small part of that, but we spent a year tracking down what was going on and try to solve it. What we did is we actually created on a large board a simplistic analysis that is a analysis kind of like this idea, but a lot more sophisticated of all the ground circuits until we could find out who was doing what to who. And as a result, by solving that dilemma, we were able to deal with how to modify the ground system so the tickle box didn't get quite so upset. So anyhow, this is used in engineering practices. In fact, if you want to do an in-depth study on transistor analysis or tube analysis, there's also a similar equivalency used there. You've heard with transistors on hybrid parameters, perhaps. And transistors before hybrid parameters, there was R parameters. That was the first ones. And then later they decided to go to hybrid parameters. If you ever want to pursue that sometime, I'd be glad to do so. All right, let's stop here for a minute and I want to show you something else. But questions first of all. I'm looking to see how glassy-eyed you guys are.
A little overwhelming, but I'm with Ed. I wish I'd seen this in high school.
Well,
Yeah.
This was taught in some of our more advanced courses, but yeah, not high school. When I was an instructor at Boeing, I remember hearing one of the other instructors talking to somebody else, and he said, "Oh, I hate teaching Thevenin's and Norton's equivalent circuits." And somebody else said, "Why?" And he says, "You go through all the proper procedures and you look out there and you got a whole bunch of glassy-eyed people." Mm-hmm. So now I'm going to show you a little bit more on this. There's something else. See if I can find the right drawings here. Here we go. Look at this. I'm going to show you, this is really important. One of our analysis that comes out of this something that we don't see in this circuit, but we could do it by measuring. Actually, you could breadboard it and experiment with it. Here's what you're going to find. If this is an open circuit, then the maximum voltage will be this 1.407 volts. There it is. If you were to put a dead short here, it is this voltage and this resistance that determines the maximum amount of current, which turned out to be 91.7 microamps. Now, if you can kind of read ahead for where I'm going on this, you can vary this resistance all over the place. And as long as these are linear circuits, no reactance, no inductance, no capacitance in here, strictly linear circuits, it will follow a straight line. And this is our maximum limit. So here is the maximum voltage we'll see, and this is the maximum current we'll see. With anything you plug in here, anything at all, I don't care what it is. Whatever you have, whatever you adjust this, it will follow this line. So all of a sudden we've learned something. Now with our equivalent circuit, we can determine these values. We can determine them by simple calculations now. All of a sudden, what we thought was a complex circuit, we're having to refigure everything over here, suddenly becomes a very simplistic. I think that's the marvel about this, is we've gone from very complex, a lot of calculations, down to piece of cake. That's it. Maximum values, maximum voltage, maximum current. By the way, in a lot of places, this would be called the load line. Isn't it neat? I think this is one of the neatest things that there is. Now, consider this. Remember a while ago on conductance and resistance, I was talking about reciprocal relationships. There is a reciprocal relationship here. Let me show you what it is. Suppose I put this problem up on the board and I, instead of putting 3.9K, I put a dead short between these two terminals. And then I put it up there and I say to the class, okay, now all I want to know is the amount of current flowing through that dead short. And you look at that and you say, sure. That's a lot of calculations to get that current. How so? Well, because this dead short means these two resistors are in series with each other, parallel with this, in series with these, parallel with this, in series with these, and got it. Now I got all the resistance. However, now I know I have to go backwards. Now I go out here and I say, okay, now I got current flow, voltage division, current flow, voltage division, current division, voltage division, until I finally get back here. Now I can figure out what the current will flow in that resistor or that dead short. Now, that is called a Norton's equivalent circuit, not Thevenin's. Thevenin's is open circuit voltage. Norton's is short circuit current. And you say, wait a minute. I get the short circuit current with my Thevenin's. You see that? I can get the short circuit current using my Thevenin's analysis. There it is, right there, plain as day. Oh, yeah, okay. What about the circuit you told me about? Oh, well, let's go to another drawing down here. Let's go to this guy. This is a different drawing, if you'll notice. Instead of having a resistor in series, it's a resistor in parallel. This is where you draw a current source. And by the way, these two circles right here is the indication for a current source, constant current source. Just like up in here, you say 18 volts. What about variance? No, 18 volts. 18 volts, that is 18.000 volts, constant voltage. Well, this guy down here is called constant current. Now let's explain what constant current is. Constant current says you do anything you want out here, you're going to get 91.7 microamps regardless of what you do. That's going to be it. This guy here delivers 91.7 microamps, period. You say, but, no buts, that's what it's going to be. But your resistor is here. If you have an open circuit, guess what? It all goes through that resistance, and that develops an open circuit voltage out here. What happens if you have a dead short out here? In a dead short, all that current goes through the dead short and none goes through here. And guess what? It's still the same chart that travels in that diagram. Same thing, except here you're doing what they call a current analysis, which is called the Norton's equivalent circuit, as compared with the Thevenin's equivalent circuit. So you have EOC for Thevenin's, you have the ISC, short circuit current, all from the same thing. One is a reciprocal of the other, if you want to look at it that way. Now, comments, questions. Are you still with me, or did I lose you around the last turn?
Dave, the name of that upper one you said is called Thevenin's.
The first one was Thevenin's.
Could you spell it?
Yeah, right here, Thevin. Let's come back here and look at it here. Here it is, Norton's equivalent circuit analysis. Thevenin, here it is, right here.
Gotcha.
Thevenin's
Okay.
equivalent circuit analysis, all right?
Okay.
All right, and then the other is Norton's equivalent. What happens is there's two different ways of looking at the same thing. I'll give you an example why this is so important. When you get into, let's say, transistor circuit design, there's three different configurations for a transistor, as an example. Same thing as with tubes. You have a common base, common emitter, common collector. The characteristics of that transistor varies considerably depending on the way you structure it, whether it's common base. As it turns out, a common base transistor has a constant current configuration. Whereas if you have a constant, that is a common collector, which becomes an emitter follower, now you've got a common voltage device. So it really is a voltage source, constant voltage versus constant current. As it turns out, a transistor in a common base configuration, it will deliver a current which is just, it's where you told it to be, and you can change your load all you want. And it says, I don't care what you put out there for a load. So this is something that'd be good to go through sometime, if you, and I would enjoy doing it if you want, on transistor design. And then predictability, interchangeability, these are all factors that can come into play with just a single transistor design, if you will, circuit design. And I have material already made up for that if you're ever interested in. All right, now I got something else to show you. You see this ladder circuit computation. Do you see this?
Yes.
This is downloadable. I guarantee you it has no viruses. However, if you try to bring it up with Windows, they'll say, oh, it's not safe. It is, it's safe. You just have to work at it. This is that same ladder circuit. Let me show how it works. Okay, over here on the side are all the values. And these values from here are what's going to be transferred to there. Here they are. Okay, you say, now what? Well, watch this. Remember, we took these guys and added them together in series. Okay, look here. They all compute down to this as a series value. Then you go to the next step. You say, okay, now that is going to be parallel with this guy. Oh, let's see what it is. Ah, there we are. That's your parallel value. Put that in series with those, and bingo. Put that in parallel with that, and then in series, and there's finally your total. And guess what? We can now figure out a current. You say, okay, now what? Well, now what we can do is start expanding that. This guy here will expand out. So you click on, there we go. Now we got all three of them out there, including this one we had a while ago. We can do the next step, square it out. The next step, square it out, square it out, square it out. Bingo. Now I got all my voltages and all my currents. If you want to cheat, well, we can do it that way too. But also, let me show you one more thing here. I can also come down here, see, and I can say, how much power? Oh, there's my power. I see. By the way, all programs seem to have bugs. Like I'm missing my power for this guy right here. However, let's do this. Let's come back here and let's say, oh, I don't know. I could do this. I could say, first of all, restore the originals. And, oh, wait a minute. Let's do one more thing. Remember I talked about Thevenin's? Guess what? EOC. Watch. Bingo. There's my EOC voltage. And then how about all these resistor values computed up? Oh, bingo, there they are. And look, I'm building a circuit down here, and there we are. Here's my voltage. There's my resistance. And then here's my 3.9K sitting out there, and there is the values. And what about on the Norton's, which is the short circuit current? Well, I can come over here and click on that. And now what I have is short circuit current. you'll find that all the collective resistances are the same because you measure them with an ohm meter. And then here is my circuit down here. Okay. Now, what you can also do is you can say here, I can compute, let's see, let's do one more thing. Suppose that as the instructor says, I want to change this 3.9K to something else. Well, here it is right here, 3.9. You can't change it there, but look here. You click on the button in front that turns gray. Now I can put in 6.8. Come up here and transfer those values. And I can compute all values. And there we have our 6.8K and a whole new set of readings. Now, my point is, this guy here is free. You can take it. I release it to everybody. You can use this to compare. If you're ambitious enough to go ahead and calculate some of those, you can use this to see if your answers agree. All right. Change anything you want. I can even change this 18 volts. I can say, what would happen if I put a, let's say a 9.1 volts there? I can transfer all those and recompute them, and bingo. My voltage has changed because I changed my source voltage, which is sitting over here in this area. And this is the current. So if I had a 9-volt battery sitting here, that's the amount of current coming out of that 9-volt battery until it dies. This is available for free. Bear in mind that even though I spent a lot of time on it, who knows what kind of errors I've left in there that I don't know about. But let's do this. Clear all computations. I can come up here and I can say, transfer the values, compute everything. Bingo. There we go.
Where was the compute? Oh, compute.
Right here, clear all, and then
compute all.
So it's transfer and compute. And if you want, let's clear these again. Instead of going through a step-by-step process, I can do this. I can jump down and I can say, well, compute all the way down, if you will. These are step by step, right? And let's do the clear. Here is turn on. These are the equivalents. These greens here, these are the equivalent circuits. So wherever I figured, like these 3 resistors in series came out to be this value here, the equivalent. So this is equivalent number 1. Here's equivalent number 3 and 2. By the way, you can do all this on a spreadsheet, but I kind of like the visual myself. This was done with Visual Pascal called Delphi. You can do it with Python. You can do it with any number of languages, but I like the visual.
Nice.
And feel free to download it, play with it. It's a lot of fun.
I've got it. It's working.
Okay. You did it already? Okay.
Oh, yeah. Oh, yeah.
Okay. All right.
You changed your mind. I wanted to get it in there.
No,
I'm just teasing.
Yeah.
That's really clever, Dave. This is,
well, thank you. It's
how great this would be to be a student, work it all by hand.
Oh yeah.
Grasp on it, and then really go crazy with the program.
Yeah. By the way, I've done the same thing with my transistor design circuit, both in pre-analysis, pre-design, and post-design. And I have a diagram which shows all values and change in parameters in much the same way as this. And it's free too, for anyone that wants to go that way.
Yeah, thank you. That's really
That's
cool.
on your site, Dave?
Yes. Well, actually,
it's on the bottom of that page.
I can put it on the site. I don't think I have it there, but not in this location. I can. So a year ago, I had a couple of students that really wanted to get into understanding transistors. And so I developed it as we went, and including the diagram. So, and I welcome any kind of comments or such. I try not to be thin-skinned.